here we've got a range of what we call our breaker products. Now they come in a wide variety of different form factors, but they're all very similar. They go between a device and the host it would normally plug into. On each one, we have switches on every important pin of the connector. So we can control power, we can control the high-speed data lanes, or we can control the sidebands. So for instance, this is a standard enterprise drive. I can pull it out the enclosure. I can plug a breaker on the back. I can put it straight back in again. And in seconds, it's ready to go. Now, this would plug into our controller. And with that in place, you can then automate testing on the drive, both to do things like hot plug, to remove and insert this drive into the system. So no more physical interaction by a technician. It can be done automatically via a script. You can also, for instance, cut individual ports, cut individual lanes. We can cut one power rail while leaving another connected. We can even inject physical errors onto the data down to around 50 nanoseconds. So we can take out just a few bits of data, and all of this can be done to see how the system responds.
So who would do these tests?
Hopefully anyone who's designing an important data storage system. So if you're going to make something that goes into a home PC, if you have to turn it off and on again, it might be annoying, but it's not going to be a big problem. If you're in a bank and you have hundreds or thousands of drives containing your important data, over time, some of them will fail. Someone's going to have to come along, they're going to have to pull a drive out and insert a new one. And it's absolutely critical that that happens correctly every time. No loss of data, no shutting down the machine, no unwanted errors. It needs testing.
So you said that we could cut signals. So what kind of testing might that be useful for?
In the simplest form, it can be turn the drive off. Then does the system identify the drive is gone? Does it, in a multi-drive RAID system, does it correctly fail over? Does it take the actions that are necessary to deal with the drive that's failed? Does it tell someone about it? But we could be looking at a more complex case. So on a drive, for instance, there are many different electrical contacts. Any one of these at any time could fail. You've got these systems, they're in a rack, there's vibration from fans, they could be in there for years. Sooner or later, something's going to fail. One pin fails, what happens? Does your system identify that drive as bad? Does it flag it up for it to be changed? Or worse, do you lose data? Or does your server just shut down?
And I guess a failure might be intermittent, or it might be hard.
A failure could be intermittent, and we can generate intermittent failures with this in a way that would be extremely hard to duplicate by other means.
So I guess if I was a firmware engineer and I was trying to make new releases for this drive, I might be able to then use an automatic test script to test each revision of my firmware and check that I haven't introduced new.
You absolutely should, and the idea behind all this is automation. So it's always possible to create a test and run it, but it could take several hours to set up an individual test setup where you want to create one specific failure. With this, you can build up a suite of tests, you can run them overnight, and as you say, Mike, every time you have a new piece of hardware, a new firmware release, you can run all those tests again and verify that nothing's changed.
And I guess it's not just firmware, right? The system designers also need to be able to do that.
It's needed the whole way through the stack. Everything from the power management circuitry on the drive that has to survive power cycles, it has to start up correctly, to the firmware on the drive, to the RAID software running between the drives, the system management software that's reporting on the health of the entire server. All of that will interact with the communication path between the disk and the drive. And this is just one disk. We've got more form factors here.
So that's a 2.5-inch drive there, and there are some more modern form factors coming along. So here we have a PCIe NVMe SSD. So this might go into a high-end server. Same idea. What we can do is we can take a breaker. This one looks a little different, but it's the same idea. And we can plug that in to our host, plug the device on top, and now we have the ability to cut power to the device, we have the ability to cut lanes to the device, and we can simulate different scenarios and different failures.
Exactly, and this device could have up to 16 different lanes, so there's even more things that we can fail there in different ways.
And these interfaces are getting faster and faster, which gives you some unique challenges as well, right? So this is a Gen 6 breaker, so we have 64 gigabit signals going over this, and so it must take some nifty design work.
It certainly does. We've got to be as transparent as possible. So the aim here is that with our device in between, we don't retime, we don't redrive the signals. We have to be completely transparent. So with our device in place, the drive and the host have to communicate together exactly as they would without us there.
As we get into a world, so many of our customers find that they don't necessarily have the right host in the right place, and they tend to use adapters. And so they might use, in this case, is a PCIe to EDSFF adapter. And so we've integrated our breakers onto some of these adapter boards as well. So in this case, we have what we call a hybrid. So we've gone from an AIC, so PCIe slot on the bottom, to an EDSFF drive. And that allows us to replace some of our customers' adapters and reduce the risk of there being signal integrity issues within their test process.
Exactly. And because we've got a bit more space on this board, we've integrated our power analysis electronics on here as well. So not only can we do the hot plug and fault injection tests, but we can look at exactly how much power consumption the drive's using at the time. We can even tap into most of the digital sidebands to look at things like the reset signal, clock, rec and wake, look at what the device does when it powers up, which can give you a really good hint when you're bringing up new devices as to why they're not actually working reliably.
Many, many times we've had customer cases where the timing between power burst and clock reference clock has been problematic because you develop the device in one system, you take it to your customer, it doesn't power up. And why is that? It's because the clock was asserted a little later. We can both test that and we can see that in this device, which is hugely valuable to our customers.
Then we've got a few other form factors as well. These are breakers. We call them cable breakers because rather than going between a device and the host, you're going into the cable path. So this is for USB 3.
This is for Ethernet. So we can do up to 10 gigabit Ethernet. We can break again in exactly the same way. So the nice thing about our breakers is that they don't care about the protocol. They care about signal integrity. So the same device works for 100 megabit, works for a gigabit, works for 10 gigabit. And again, in the other ones, we go from 3 gigabit right up to 64 gigabit now. And the interface looks the same. So I can develop tests for PCIe and I can apply them to SAS. I can then apply them to Ethernet. And everything stays the same, which is very helpful when you're trying to keep your development time down.
We attempt with these breakers to cover every removable part of the system. So whether it's a slot, whether it's a drive, whether it's M.2 or a cable in the back of the system, the idea is to be able to instrument any part of it. So whether you have a drive or whether you have a server with many different cables and points, we can instrument all of them and expand your testing.